Hey everyone! Welcome back to the ECS video series. In the last video, we explored everything you need to know about load balancing in ECS, the concepts, the components, and how traffic flows between your services and tasks. If you haven't watched that yet, make sure to check it out, the link is in the description below. Starting from this video, we're moving into the hands-on section of ECS load balancing. In this episode, we'll walk through how to integrate an application load balancer with the EC2 launch type, so you can see how load balancing works behind the scenes. Alright, let's jump into the hands-on part and see how this works in action. Before we jump into the hands-on part, let's set things up properly. For this video, I've created a new branch called ECS load-balancing. Make sure to check out this branch, because this is where we'll generate our new Docker images and work through the load balancing setup. Now, before diving into the actual configuration, let's quickly go over the new changes I've made to our previous code base. This will help you understand exactly what's been updated and why, before we move on to the implementation part. First, open the project in Visual Studio Code and make sure you're on the correct branch. In the index.js file, I've added two new routes, a health route and a metadata route. Let's start with the health route. This is a simple endpoint we'll use to verify that the application is running properly. This route is important because the application load balancer will use it to check if the container is healthy. The response should be very lightweight and quick to return. It's not meant to perform deep system checks or database queries, just a basic confirmation that the service is alive and responsive. Next, let's talk about the metadata route. This one is more interesting. The metadata route pulls information from both the ECS task metadata and the EC2 instance metadata and sends it back to the frontend. We'll use this data to identify exactly which container handled each request once we integrate the service with a load balancer. That way, when you refresh your browser, you'll see which container instance is serving your request in real time. Here's how the metadata route works. When a container runs inside ECS, Amazon automatically injects a metadata URL into the container's environment variables. This URL points to a local endpoint inside the container, which can be used to retrieve runtime information about the task, such as the task ID, launch type, and more. This URL is only available inside the container environment, you can't access it from outside. So in our implementation, the first thing the route does is check whether that metadata URL exists in the environment variables. If it does, we send an HTTP GET request to that URL to fetch the metadata. The response is a JSON object that contains detailed information about the running ECS task. From the metadata response, we extract two key pieces of information, the task ID and the launch type. The task ID actually comes from something called the task ARN, which stands for Amazon Resource Name. An ARN is a unique string that AWS uses to identify resources across different services. In the case of an ECS task, the ARN is made up of several components such as the region, account ID, cluster name, and the unique task identifier at the end. In our metadata route, we take that final portion of the ARN, extract it, and send it to the frontend. We also extract the launch type, which tells us whether the container is running on EC2 or Fargate. Now, if the launch type is EC2, that means the ECS task is running on an EC2 instance instead of Fargate. In that case, we can take things one step further and identify exactly which EC2 instance the task is running on. To do that, we first extract two values from the metadata, the cluster name and the task ARN. The cluster name is usually a simple string that represents your ECS cluster. The task ARN, or Amazon Resource Name, is a long unique string used by AWS to identify the specific ECS task. Once we have both the cluster name and the task ARN, we can use the AWS SDK for JavaScript, specifically the ECSClient, to query more information about the task. Using the describeTasks command from the ECSClient, we can retrieve detailed information about that particular ECS task. From the describeTasks response, we can extract another important value called the container instance ARN. This ARN uniquely identifies the EC2 instance that the container is running on within the ECS cluster. If a container instance ARN is present, we can then use another ECS SDK command called describeContainerInstances. This command takes the cluster name and the container instance ARN as inputs and returns details about the underlying EC2 instance. From that response, we extract the EC2 instance ID, which tells us exactly which EC2 machine this container is running on. Finally, the metadata endpoint compiles and sends three key pieces of information back to the frontend: the launch type, the EC2 instance ID, and the task ID. This data will be displayed on the frontend so we can clearly see which ECS task and which EC2 instance handled each request. Next, in the index.html file, there's a function called fetchMetadata. This function is automatically triggered when the window finishes loading. Inside this function, we make a request to the metadata endpoint that we just discussed a moment ago. The function fetches the metadata response from the backend. Once the data is received, it's displayed directly on the web page. Alright, now let's build our Docker image and see what it looks like. First, navigate to the project's root directory and paste the docker build command. You can find this command in the GitHub repository. Once the local build completes successfully, run the docker images command to confirm that the new image has been created. Next, let's run the Docker image locally to verify everything is working as expected. When you start the container, the application will run on localhost port 3200. Once everything looks good, stop the running container and do a quick Docker cleanup to remove any temporary or unused resources. Now that our local build is verified, let's move on and create an ECR repository. After creating the repository successfully, list all ECR repositories to confirm that it's available. Make sure you're authenticated to the default AWS registry before pushing images. You can find all these commands in the GitHub repository. Next, let's build a multi-platform Docker image, which ensures that our image can run across different environments. Once the build is complete, push the image to the ECR repository we created earlier. After the push finishes, list your Docker images once again to verify that the upload was successful. Navigate to the ECR console, go to Repositories, and you'll see the latest Docker image you just pushed listed there. Now that the image is ready in ECR, our next step is to create a new VPC. Head over to the VPC console and click on the Create VPC button. Give your VPC a clear, descriptive name. Set VPC endpoints to none, and leave the rest of the settings as default. Then, click on Create VPC to finalize the setup. Once your VPC is created, we need to enable auto-assign public IPs for its public subnets. Select the VPC you just created, go to the subnets section, and edit the two public subnets. Enable the auto-assign public IPv for address option for both and save your changes. Now that our VPC is ready, the next step is to configure Amazon ECS. Navigate to the ECS console, click on Clusters, and then select Create Cluster. Under the Cluster Configuration section, give your cluster a clear and descriptive name. In the latest AWS console UI, AWS has updated the cluster infrastructure options to give you more flexibility and control over how your cluster is managed. These include Fargate only, Fargate and managed instances, and Fargate and self-managed instances. Fargate only means your cluster will run entirely on AWS Fargate. Fargate and managed instances gives you a mix of Fargate tasks and AWS managed EC2 instances. In this mode, AWS provisions and maintains the EC2 instances on your behalf. And finally, Fargate and self-managed instances, previously known as the EC2 launch type, allows you to use your own EC2 instances, giving you full control over the underlying infrastructure. For this video, we'll stick with Fargate and self-managed instances, since we're demonstrating how load balancing works with EC2. Next, under Capacity Settings, leave the default EC2 instance type as it is. It's more than enough for this demo. Set the minimum capacity to 2 and the maximum capacity to 3. Then, select your SSH key pair if you've already created one. This will allow you to connect to the EC2 instances later if needed. Under the networking section, choose the VPC you created earlier and select the two public subnets. Next, create a new security group that allows inbound traffic on port 3200 from anywhere. This is the port where our Node.js application is listening. With all these configurations in place, click on Create Cluster, and AWS will begin provisioning your ECS cluster. Once the cluster has been created successfully, navigate to the Task Definitions section to create a new task definition. Give the task definition a clear and descriptive name. Select the launch type as EC2 instances, and change the network mode to host. Set the memory size to 1 GB. Under the Container Details section, give your container a meaningful name. Select the ECR image we pushed earlier from the pop-up, and configure the port mapping so that the container port 3200 maps to the host port 3200. Give this port mapping a descriptive name as well. Set the CPU to 1 GB, the memory hard limit to 1 GB, and the memory soft limit to 0.5 GB. Once everything is configured, click Create to create the task definition. After the task definition is successfully created, click to go to the Create Service page. Give the service a proper name, select the launch type as EC2, and set the desired task count to 2. We need a minimum of 2 tasks to demonstrate load balancing later. For now, we will leave the load balancing configuration and click Create to launch the ECS service. Once the service is created, let's locate the public IP of one of the running tasks and open it in the browser to see if our Node.js application is working. As you can see, the app is running, but the configuration data is not loading. Navigate back to the task configuration and check the Logs tab. It looks like the EC2 instance role does not have permission to perform the describeTasks action. To fix this, navigate to the IAM console and click on the EC2 instance role. Click Attach Policies, search for the Amazon ECS Full Access policy, and attach it to the role. Once the policy is attached successfully, return to the task page and refresh it. Now you can see that the configuration data loads correctly. The page shows the launch type as EC2, the task ID, and the instance ID. Open the public IP of the other task in a new tab to compare. You can see that the two tasks are running on two different EC2 instances and each has a unique task ID, which matches what we see in the ECS console. Similarly, the EC2 instance IDs match the actual instances running in your EC2 console. This confirms that everything is working correctly and our tasks are running as expected. Now let's integrate an application load balancer into our ECS service. Navigate to the Load Balancers section in the AWS console and click on Create Load Balancer. Select Application Load Balancer, then give it a proper name. Choose the VPC we created earlier and select the two public subnets. Next, let's create a new security group for this load balancer. Give it a meaningful name and description, select the same VPC, and under Inbound Rules, allow HTTP traffic on port 80 from anywhere. Click Create Security Group. Return to the Application Load Balancer console and select the security group we just created. Now, move to the Listeners and Routing section and click on Create Target Group. Leave the target type as instance, give the target group a proper name, keep the protocol as HTTP, and set the port to 3200. Select the same VPC, and under the health check settings, include the proper health check path. In the next step, select the two EC2 instances that were created by our ECS cluster and register them under this target group. Then click on Create Target Group. Once created, select this target group from the drop-down, leave the remaining configurations as default, and click on Create Load Balancer. After the load balancer is successfully created, navigate back to the ECS console. Select your ECS service and click Update. Scroll down to the load balancing section and expand it. Click on Use Load Balancer, choose the same VPC, then add the load balancer we just created. Select the appropriate listener rule and target group. Once everything is in place, proceed to update the service. You can find the load balancer's public URL from the EC2 console. Open that URL in a new tab, and when you refresh the page, you'll notice that the instance ID and task ID keep changing. That means our application is working correctly, and the load is being distributed between the two running tasks. Alright, that's it for this video. In the next video, we'll dive into load balancing using the Fargate launch type. Stay tuned for the complete ECS video series, there's a lot more to come. Thanks for watching, and if you found this video helpful, please leave a comment and share your thoughts below. I'll see you in the next video.